Questions on the ODP you just turned in? So let's just eyeball the code. .203 you just turned in? Yeah. So so there's a valid get node function. So again, you've got to tell the system what a struct node is before you try to use it. So very beginning of the file, struct node, write it out, semicolon at the end. And then the function is called get node, takes an array of struct nodes, which I called LL. And then it's just a loop through all 100 elements. And for each element I, check to see if the valid flag is equal to 0. As soon as I find the valid flag is 0, I'm done. I can return right then and there. Okay. Now I could try to save it in a variable, and at the end of my loop, see if that variable got set. But that's more confusing than it needs to be. The only thing I care about is there a valid flag that's equal to 0? And if there is, as soon as I find it, I know what I want to return. I want to return that index. So I'm just going to do my return I right there. And that also tells me that if I come out of the for loop, I did not return, I did not find a valid flag of 0. Immediately I know, okay, there's no space left, so I'll do my return of -1. Okay, and indenting, right, helps me keep track of what's inside what. So I know this return -1 is outside of that for loop. If everything is left justified, it's not always clear what the indenting is. Thanks. So that's a get node function. So ODP 204 is not actually part of PA1, but it's doing things that are similar to what you're going to need to do in PA1. So 204 is a function that's supposed to take a linked list implemented in this form, right? So an array of struct nodes with a sentinel node at index 0, and then links where the next field points to the next node's index, and so on. It ingests a linked list in that format, and it returns the first data node's value. So if we pass it a linked list like this, getFirst should return the integer 10. Okay, it's returning the value of the first data node. If the sentinel pointed to a 20, then getFirst should return a 20. The trick is, if our list is empty, there is no first node, right? The sentinel is not considered a data node in our linked list. So if we pass it a list that's empty, what should getFirst return? And since it's returning an integer, there's no magic value we can use to say, hey, we got an error, there's nothing in the list. Because, you know, our first node could contain a -1. So if I return -1, how do I know whether that's an error or whether my first node was -1? So to be able to distinguish the case where there actually was no first node, we need a separate variable. So that's what the second parameter called error is. Okay, error is an integer whose address we pass to getFirst, and getFirst will fill a value into this variable. So here's the deal. If there is a first node in the linked list, error should be set to 0, and the function should return the data value of that first node. In the case where the list is empty, error should be set to 1, and the function should return a value of 0. All right, so two different behaviors that getFirst can do. Pass it an array of linked lists and pass it the address of an integer. And it either sets that error to 0 and returns the value of the first data node, or sets the error to 1 and returns a 0. Yeah?
So in the first case, it returns the value of the data, not the index.
Not the index, the data value itself.
So, in terms of if the first node is empty, is that determined by the next of the sentinel pointing to something specific, or is it determined by the data value that next is pointing to having a valid of 0.
It's indicated by the fact that the sentinel node's next value is equal to my null, minus 1. Because there are no data values that are special, right? Any data value is legal. Any integer is a legal data value. So we have this pointer basically to my null, which says there's nothing after this node. So here's our getFirst function. Gets a struct node array called LL, gets an integer pointer called error. You do some stuff and you discover the list is empty. Here's what you do. Set star error equal to 1. Right, it's star error because error is not an integer, it's an address of an integer. So star error says the thing pointed to by that address. The parentheses are optional, but they let you see more clearly maybe that this is the thing that's being set to 1. So this says set error flag to 1 and then return 0. Because it says to return a 0. Otherwise, you do some stuff, and let's say your first data value is n. So star error equals 0. It says clear the error flag, and then return n. So just a reminder how you deal with these pointers to integers. And in your main program, you have some variable, I'm just going to call it ERR, which is declared to be an integer. Don't declare it to be a star int. Because inside main, we want to actually have this variable exist. We want space allocated for it. So I'm going to declare it to be an integer, but then I'm going to say something like result equals getFirst list, comma, ampersand ERR. That says pass the address of that variable. And so inside here, error would be the address of this variable in main. And when I say take the thing pointed to by that and set it to 1, it actually sets this variable in main equal to 1. So now when I want to test this, I can call my getFirst like this. I can print out the value of ERR. I can print out the value of result. And then make sure it does what it asks you to do. Is that clear? If you haven't messed with this before, right, this is a good chance to mess with it. And we'll be playing with pointers more in a week or two. And so this will become old hat to us.
So if there isn't anything else, the next value of the sentinel is going to be -1.
Correct, yeah. All right, thank you for all the GitLab repositories and all the additions as a reporter. I got like 20 billion emails yesterday from people, so awesome. Good to have that set up and ready to go. All right, so let's talk more about PA1. So you know the basic setup. You're implementing a linked list using an array of struct nodes. You're making various routines that will be used to interact with your linked list, and then you're writing a main program to take commands from the user and let them interact with the linked list. And I showed you the sample program yesterday, right? We ran through it. Okay. So let's talk about how to develop this. You've already got an init. You've already got struct nodes. You've been writing those all week. You've got an init function, which initializes an empty linked list. I would make an add function, but make yourself a simpler add function. Make yourself an add function that just adds to the beginning of the list. Forget about keeping things in sorted order. Make an add function which will do the following. Here's my sentinel. And maybe that points to a 10, and that points to a 20. And if I say add 30, it should make a new node 30, have the sentinel point to that, and have the 30 point to what was the beginning of the list. Okay, that won't get you full points for PA1, but this is for development purposes only. If you can write code that will add a node to the beginning of the list, you're like 90% of the way done with your add function. All the hard work in this, dealing with this array of structures with these different fields and knowing how to check the valid flags and all that kind of stuff, you got to do all of that to make this work. Okay? But this is easier because we always know where we want to insert. We want to insert right after the sentinel, and we want our new node to point wherever the sentinel was pointing. So add version 0 n. Well, if we have a list and we want to put a new node in the beginning, let me make you a nice list. Here's our sentinel. Points to a 10, points to a 20. And let's say our sentinel is 0. I'll put my magic 42 in there. And let's say that 10 is stored at location 2. And location 2 is our 10, which points to location 1, which is our 20, which points to -1. So there's a list with a 10 and a 20 in it. Okay, I want to make a new node 30. Find a new spot. Okay, that's your getNode function. It should tell you that index 3 is available. Set the data field, list bracket, whatever getNode return dot data equals 30. Set its valids flag should be set to 1 in your getNode function. Right, so you shouldn't have to do that outside. And then where does this 30 go? Well, we want the sentinel to point to the 30. And we want the 30 to point where the sentinel was pointing. So the sentinel should point to 30. Well, if I is the value of getNode, right, so I is a 3, then we want the sentinel to point to index 3. So list bracket 0 dot next equals I. Sentinel points to the new node. And our new node, our 30, so our sentinel is going to point over here. Our new node should point to the 10. Well, how do we know it should point to the 10? What do we put in that temporary variable?
Whatever the sentinel was pointing to, and do that before.
Whatever the sentinel's pointing to. So our new node should point where the sentinel is pointing. Well, where does the sentinel point? It points at list bracket 0 dot next. That's where the sentinel's pointing. So let's have our new node point to that. Well, we can save this in the temporary and then assign it down here, or we can just assign it before we change this. So list bracket I dot next equals list bracket 0 dot next. So new node points where the sentinel points. So that puts this link in there. So adding a node in the beginning of the linked list, there's no looping involved. You don't have to search through and find the right spot to insert. Make a new node, okay, make sure you didn't run out of memory. Set its data value equal to n, list bracket I dot data equals n, and then do these two adjustments. Set your new node's next field equal to the sentinel's next, and then change the sentinel's next to point to your new node. Okay, now you can call add version 0 a bunch of times on an empty list and add a 20 and then a 10 and then a 30. And then print out the contents of your array. Make a for loop, print out data next and valid. And there should only be 3 or 4 valid nodes in there, right? Look at it and try to figure out what your linked list looks like. Make sure it makes sense to you. Okay, so we're not doing any parsing in main. We're calling a init. We're writing an add function that uses your get next node. And then we're just calling add 2 or 3 times. Add a 30, add a 20, add a 10, or something. And then make a for loop that prints out the contents of your struct node array. And, you know, print out the index number, the data value, the next value, the valid value in a nice table, line things up, right? And maybe just print out the first 10 entries or something. And look at it and make sure that it represents the data structure that you want it to. Okay? If it doesn't, work with that until it does. Okay, that's the place where you want to deal with misunderstandings about this. If you're getting confused between the value of next and the value of an index, or when the valid flag should be set or something like that, this is the time to figure it out. Because you're probably talking about 10 lines of code, probably less than that for your add function, right? That's where you want to figure out these sort of fundamental concepts. Once you figure that out, once you can do add version 0 and this array makes sense to you, go ahead and write print. So write a print function that will take an array of struct nodes and do what you would do manually. Start with the sentinel, look at the next field, print out that data value. Look at the next field, print that data value, look at the next field. It's -1, we're done. Once you have a print, you can make a search, because searching is a subset of printing. Instead of printing, compare the thing that you would print to what you're searching for, and if they match, return a 1. When you get to the end of your list, instead of printing a new line, return a 0, saying I didn't find your number. And once you have print, then you can work on the actual version of add, because now you have a way to look at your list without having to print out all of this stuff and draw pictures. Right? You can call your add, try to add a 10, then a 20, then a 15, call print, make sure they came out in the right order. And if they didn't, then we hop into GDB. So how do we print a linked list stored in an array of struct nodes? So let me update this to make it a little more interesting. We were putting, let me do this in the right order. So that's a 10, followed by a 20, followed by a 30, followed by a -1. So here's an array corresponding to just a 10, 20, 30. Okay, if someone handed you this array on a desert island, no computers in sight, and said, can you print out the values that are in this linked list, how would you do that? Just with this table of what the array entries are.
Start with the sentinel node, see where that points to.
Okay, start with the sentinel node, that's index 0, see what it points to a 2. So let's write some algorithmic steps. Pointer equals list bracket 0 dot next. Okay, if I go list bracket 0 dot next, I get a 2. What is the meaning of that 2? It's the next space in memory where the number is at, right? It's an index. So this is the index of the next node. That 2 means if I look at element 2 in this array, that 10, 1, 1, that's the next node in my list. Okay, first time through it's the first node, second time through it's the second node. Okay, so that's the index of my next node. I want to print out the data value. So let's just print. And the data value is, well, take the struct node at that location in the array, that's list bracket pointer, and print out its data value. All right, how do I get to the second node in the list? Yeah. So if I look at my current node, and instead of looking at the data value, I look at the next value, that'll be the index of the next node. So if I say pointer equals list bracket pointer dot next, that's the index of the next node. Maybe I should have said this was the index of the first node, which is also the next. So now pointer is a 1. That's the index of this 20. And at this point, I can just go back up here. Print out that node's data value, and then change pointer to where that's pointing.
Should this whole thing be like wrapped in a while loop that's checking to see if next dot next or whatever is set to a -1 yet?
Only if seg faults bother you. So this is a loop that will run forever, and it will seg fault when it gets to the end of the list. So we need to have some kind of condition. So what would be a good condition for the while loop? How would we know when we're done with this list?
While not done.
While not done. Cool. All right. So how do we set the not done flag?
While not equal to my null.
Well, what's not equal to my null?
Oh, yeah, my null. No.
Yeah, -1, my null.
Pointer.
Pointer.
Next.
So if we're thinking of PTR as the index of the node that we're about to print, okay, up here PTR was the index of a node that we were about to print. Down here I changed PTR, that's the index of the node that I'm about to print. Okay, so I'm going to throw a little comment in the beginning which says PTR is the index of the next node to print. Well, if that next node is not something that exists, that's when we're done. What does it mean when we say that next node doesn't exist? It means that its index is my null. So this whole thing could be while PTR is not equal to my null. And when we come out of that while loop, let's just print a \n and return. Okay, so let's check this. Here's our linked list. We're going to start off with PTR equal to list bracket 0.next. That's a 2. Okay, 2 is not equal to my null, so we're going to print list bracket 2.data. That's a 10. So what are we printing? We print a 10. And then we see PTR equals list bracket PTR.next. Well, list bracket 2.next is a 1. So PTR changes to a 1. We come back to the top of the loop. That's not equal to my null. So we're going to print list bracket 1.data. That's a 20. So we print a 20. And then pointer equals list bracket 1.next. List bracket 1.next is a 3. Top of the loop. 3 is not equal to my null. Print list bracket 3.data. That's a 30. Pointer equals list bracket 3.next. That's a -1. Top of the loop. Pointer is equal to my null. We're going to exit the loop. We're going to print a new line. And we're going to return. And we printed the list successfully. So in this case, looks like the code works. What about if the list is empty? What if the Sentinel node has a next field of -1, which is an empty list? Well, pretend you're a computer. PTR is going to be equal to list bracket 0.next. So first time you come into here, pointer is going to be equal to -1. While pointer is not minus my null, pointer is equal to my null, so we're not going to do this while loop. First time through, we're just going to come straight down to the bottom. We're going to print a new line and return. That's exactly what we want. So it works for 3 nodes, works for an empty list. You could try it for 1 node, or believe that this is going to work. Okay, so what did we do? We made a list. We created an array that corresponded to the implementation of that linked list. We thought about how to print it as a person on a desert island, what steps we go through. We wrote down some pseudocode corresponding to those. We added some variables and we wiggled around with this a little, and we figured out how to stop it from blowing up and so on. And then we tried it. We pretended we were a computer, and we went through this code and we looked at what it would print. If you do all of that and it looks like things are good, now you hop into the editor and you start writing some C code. And you write C code that corresponds to this. Well, a lot of this looks like C code already, but it's not always going to look a lot like C code. And you got to add semicolons and parentheses and double equal signs and so on. You write the code, you compile it, and then what do? You run some test cases. Well, how do you make a test case? You've already got an array of struct nodes, right? Struct node list bracket 100, put that in your main program. How do we make our linked list? List bracket 0.data equals 42. List bracket 0.next equals 2. List bracket 0.valid equals 1. That's this first row. Putting this back to a 2. List bracket 1.data equals and so on. List bracket 2.data equals and so on. Right? If you trust your init function, call init ahead of time. That'll clear out all the valid flags. And then just set explicitly what you want each of these fields to be equal to. If you're only making a list with a Sentinel and 3 nodes, it's 4 lines of assignment statements. 3 assignments per line. This is a really good chance to practice with VI. Okay? This is kind of a pain with something like Notepad, right? It's lots of moving around with the arrow keys. VI, you can write this first line. You can just say uppercase Y and then P 3 times, and you'll get 3 copies of it. And if you start to practice with things like R, which lets you replace a single character, you can put your cursor over this first 0, hit a J, R1, J, R2, J, R3, J, R4. Use W to come over here, R4, K to go up 1 line, R3, K, R2, K, R1. Use W to go over here, do the same kind of thing. And then come down and change these values, 42 to be the data values you want, and so on. It's a really low-cost exercise to start playing around with doing more than just using arrow keys to move around and backspace to delete, right? VI, you can do CW to change 2 or more characters. If I'm sitting on the 42 and I say CW, I can type 20 escape, and it'll replace the 42 with a 20. So change the entire word. If you want to change one character like an index, just type an R, and the next character you type replaces that. HJKL let you move up, down, left, right. And you can play around with VI. See if you can make it work better for you. Okay. And once you've done this, right, maybe you want a list with 5 things in it. Well, it takes 6 sets of these assignment statements with 3 per line. But once you do this, throw it in a function. Right, my super duper init. And now every time that you're working with your linked list and you want to try adding or searching or deleting or printing or something else, right, you can just call your super duper init in the beginning of your main program, and you have a linked list, and you know exactly what it looks like, and you know exactly what the array is that corresponds to it. And you don't have to keep rewriting this and rethinking it every single time. And it will let your debugging go a lot quicker, because when you're working on your debugging of the delete function, you're not simultaneously working with how do I initialize my linked list. Right? You've already done that code and you're just calling super duper init. So play around with that if you like. And you can use that to test your print function. Set up your list, call print, and it should print out your nodes in the correct order. And when you're doing that, you know, scramble these up a little bit. Don't just do first node, second node, third node, fourth node in index 1, 2, 3, 4. Scramble them up, right? And write your init code to put them in that scrambled order. Make sure your print function does the right thing. Okay, so you've got add version 0, you've got print. Do search. Well, how do we search for something? It's just like printing. So search takes an array of struct nodes and a number, and it returns a flag, 1 if it finds it, 0 if it doesn't. So do the same thing, but instead of printing list bracket pointer dot data, say if list bracket pointer dot data equals num, return 1, because we found our number. If we come all the way through the while loop and we haven't returned, it means our number was not in the list. Don't print anything, just return 0. There's your search function. So once you got print, search is pretty easy. It's a few changes. And then you can work on your real add function if you want. You can work on your delete function, or you can do those in the other order. And you don't need a main program from PA1 to do any of this testing. Right, your main program can basically say, do your init, add a 10, print, add a 20, print, add a 15, print, delete a 10, print, search for 15 and print the return value of it. search for a 10 and print the return value of it, and so on. Just make a bunch of calls. Maybe this is this is just your plain old init, right? And don't worry about PA1's main program yet, parsing and scanf and all of that stuff, right? Just hardwire some calls and make sure they're doing what you think it's supposed to do. But before you do this, make sure your print function works, right? Because if you're getting weird results and it's a problem with your print function and you're trying to debug your add function, you're in for a long night. So try to have high confidence that print is working correctly. And if print is working correctly and you believe that add is working correctly and you're not getting the right thing after delete, right, it's probably a problem with your delete function. But if you're not sure if add is really working right, maybe there's a problem with your add function that's showing up when you call delete. So you want to really test add a whole bunch before you delete, or vice versa. All right, so let's spec out your full add function. So here's a Sentinel node, and this has got the entries 10, 20, and 30, and this is my null. So here's an example of a linked list implemented with this array that has a 10 and a 20 and a 30. And we want to add some number to our linked list. And for the real version of our add, we want to keep our list in sorted order. So suppose we want to add 25. Okay, by looking at this and being smart humans, where should the new node 25 go in that list? It goes after the 20 and before the 30, right? But if we're not a smart human, how do we know that that 25 belongs between the 20 and the 30? How would you explain this to a computer?
Search the data until you find a number that's bigger than that.
Search the data from the beginning until you find the number that's bigger than 25. The first number you find, you want to insert right before that. So find first node with data bigger than num. All right, and there's one little detail here. If we move through here and we get to this node and we say, okay, that's a 30, that's bigger than num, we still need to know what the previous node was, because that's the one that we're going to have to change to point to our new node. So I'm going to modify this and say find first spot where the next node has a data value bigger than num. So I'm going to start off with something that's equal to 0. That's basically pointing to our Sentinel. So current index equals 0. I'm going to ask the question, should we insert immediately after the node stored in index, current index, right? I'm always thinking about the linked list. Should we insert immediately after the node specified by current index? Well, the way we would know that is next index equals list bracket current index dot next. So if this is current index, next index is the index of the following node. So if list bracket next index dot data is bigger than num, then we want to insert after current index. And when we're done, return. Otherwise, we're not inserting right after current index. Maybe we want to insert after that following node. So let's change current index to be that following node, next index. And let's go back up here. So we basically change this to be current index, and we change this to be next. And next data is not bigger than 25, so we're going to change this again to be current and next. And now next data 30 is bigger than 25. We want to insert right after current index. So now you do the thing we've been doing with the pointers. Change list bracket current index dot next to be the index of this new node. And change this new node's next to be whatever next index is. And before we do any of this, we have to say new node index equals get node. Right? Call the get node function to get the index of a new node and set the data equal to num. And get node should set the valid flag for you. And so down here, make this adjustment on the next field and return. Otherwise, move down the list. Okay, so when do we stop? Because this is an infinite loop. And it's possible that we're inserting after the last node. In that case, current will be the address, the index of the last node. Next index will be my null. And if we get to that point, we don't want to continue looping. We just want to go ahead and we want to set current index to point to our new node, have our new node point to my null, and return. So that's an edge case. So again, don't worry about the code itself. Think about the procedure, right? Come up with a set of steps you can use on this data structure to say, okay, this is where I'm going to get to, this is what I'm going to change, and so on. Write some pseudocode to do that. Play around with it, make yourself a few lists, a few array implementations, run through this and make sure it's working in all the test cases. And then write it into code, compile it, write some test programs, see if it looks like it's adding correctly. Right? Add some things, print them out, make sure when you take your data and you turn it back into a linked list, it's sorted. All right, we'll talk a little bit next time about the main program. The main program is pretty straightforward. It's another version of what you did a bunch of times in 224. Right? Print a prompt, do an fget, do a bunch of scans. All right, I will see you next time. Have a good weekend if I don't see you in 215. And start working on PA1 if you haven't already.
So I didn't read the sign-in sheet the other days before I
That's
signed
okay.
it. I didn't.